Alrighty, so in this video we're going to discuss the beginning of coordinate transformations. This is very, very important in physics because when we get into very complicated problems, or even not so complicated problems, but ones that are more real world, oftentimes the mathematics behind it can get a little complicated, a little complex. And if we rearrange or kind of modify how we define particular things in the math, we can find that the equations become much easier. And you'll see really good examples of this as we go along. But for now, we're going to discuss this more just as a tool that can be used, and then we'll see when should we use it, why should we even care about it. But just note, this is a very, very powerful tool, although at first, when you have to get used to it and start to either memorize or learn how these transformations work, it could get a little bit of a pain in the butt. But once you see it in action with real problems, you'll see why it's such a good thing. It's actually very, very beneficial to you because, for instance, if you want to try to functionally define something like a circle or a sphere, that's not the easiest thing to do with X, Y, and Z coordinates. They're our normal Cartesian coordinate system. However, if we switch to something like spherical coordinate system or polar coordinates or whatever we might be using, then all of a sudden to define the boundary of a circle, it's really easy. It's just any value of the angle. For instance, here's a circle of some radius r. Well, the boundary of the circle is for a particular value of r, equal to r, whatever it happens to be, this number, but any value of theta, you're just going around the circle, right? If theta is equal to 0, we're here on the circle. If theta is equal to pi over 2, we're here on the circle, and anywhere in between. As long as we're at constant r, then as we change theta, we're maintaining the boundary of a circle. Whereas if you tried to do this with X and Y coordinates, that's not the easiest thing to do. There's certain restrictions. For this value of X, we have a particular value of Y, but as soon as we change to a different value of Y, it's a different value of X as well. And that's not the easiest thing to do mathematically. Although we're doing the same thing, we're solving the same problem, that is to say, define the boundary of this circle, in one way of thinking, that is, distance from the origin radially outward, r, and angle swept through, theta, that's very easy to do, versus X and Y, Cartesian coordinates, it's not so easy to do. All right, so that's just a little bit of motivation. Let's actually get into how to do this. First thing we're going to do is, let's say we're in 3 dimensions, and we'll have X, Y, and Z like this. Okay, right-handed coordinate system, of course. And there's some point P. Let's do it in gray. Here's point P. And I want to locate this point P. How do I do that in 3-dimensional space? Using Cartesian. We'll do Cartesian coordinates first, and then we'll see how to modify it to do it in cylindrical. But we're going to start with Cartesian because that's what we're used to. That's what we've been doing in math since the beginning. We are always talking about X, Y, and Z. So we're comfortable with it. So in our Cartesian coordinate system, the point P, or the vector, even, we could call it like that, the vector which points to point P can be defined, some vector V, is equal to, well, it's some amount, call it, X, in the I hat direction, plus Y in the j hat direction plus some amount z in the k hat direction, right? This point P, we could see it as, think of it, remember this is three-dimensional, so it's coming out towards you, out of the screen towards you and at some angle. And we could project that point P into the xy plane. So we have a certain amount in the x direction, a certain amount in the y direction. Right, there's your y amount. Here's your x amount. And here is your z amount. Right, so this point P is over in x this much. Over in y this much, out in x towards you that much, and up, straight up, an amount z. And we could define it by the coordinates x, y, z. X in the I hat direction. Remember, I hat, j hat, k hat, those are the unit vectors. I hat, j hat, k hat. Unit vectors, also called basis vectors. They are the directions, the three orthogonal directions, which define our coordinates. So any point I put out in space can be defined uniquely using these three coordinates: an x direction, a y direction, and a z direction, and a certain amount in all three of those directions. Okay. Now, what do we want to do? Well, what is, for instance, again, if we look at our point P, then we have, let's say maybe at point P there is some electric field, or there's some magnetic field, or gravitational field, whatever it happens to be, that points in a certain direction. And the directionality is defined at this location P. There's an x component, right? So that's an I hat direction. There's the j hat direction. And there's the k hat direction. And no matter what point P we choose, so say we choose a point P that's over here now, well, at that point, again, we have the y direction, the j hat, the I hat, and the k hat. So that means our coordinate system, our basis vectors, I hat, j hat, k hat, don't change based on the position of the point we're talking about. That's very, very nice. That means no matter where I choose, if I'm locating a particular thing, I want to find what's the electric field at this location P, then it doesn't matter where that location P is, the directions, the basis vectors that I'm going to define the electric field with are constant. So I don't have to worry about, well, what is the value of the x direction if I'm at this point versus this other point? And that seems like a confusing question because, of course, it doesn't matter where you are. The x direction is the x direction. It's always that direction. That's just what we're used to because that's the coordinate system we develop all of our normal understanding. However, what we're going to find soon is that in other coordinate systems, this isn't true. It might be that whatever unit vectors we discuss, whatever our basis vectors are for these other coordinate systems, they're not going to be x, y, z, they're going to be something else. Maybe at point P, right over here, the first direction points in a certain way, but then at point, let's call this point Q over here, that same direction doesn't point in the same direction anymore and now points somewhere different. And we're going to see how that works. So that's just something you're going to have to be aware of pretty soon. We cannot take for granted the fact that the basis vectors, our coordinate system's basis, is constant no matter what the position we're talking about. Pretty soon our basis vectors will change with position. And we'll see how that works. What else do we need to do? Well, if we're doing real stuff with math, and we're talking about vectors and physics and engineering and all this kind of stuff, Likely calculus is going to be involved, which means integrals and derivatives and things like this. We're going to solve equations, and being able to solve them means we're going to have integrals to do, or we're going to have derivatives to do, or whatever the case might be. So some particular things we may want to have at our disposal are the differential elements. Differential elements. And so that's things like the differential length, dl. You know, if you have something like integral E dot dl, something like this. dl is the differential length that we're talking about. E, it doesn't matter what E is. It could be electric field. It could be some function we're talking about. But we want to do this integral. We need to know, how do we define what dl is? What is dl? Well, in the Cartesian coordinates, this is pretty easy. What we mean by dl usually means something like how far do you move in this direction? Okay. So it's a vector, which means it's got directions to it. And if I'm at point P and I'm going to change by a certain amount dl, you know, maybe point P goes from where it is here to over here, and I've moved a certain amount dl, well, that means I've moved a little bit in x, a little bit in y, and a little bit of z. And so dl is going to be, how much do I move in the x direction, I hat, plus how much do I move in the y direction, j hat, plus how much do I move in the z direction, k hat. Right? That's my differential length. I'm going to move a certain amount, a little bitty differential amount, out in space, three-dimensional space, and that differential element, how far I've moved, is a little bit in the x direction, x hat, or I hat, y, and z, of course. Okay, pretty basic. Of course, that's what it is. If I move, then I move a little bit in x, y, z. Maybe one of them 0, or two of them 0, whatever. But that's how much I move. A little bit in each direction. Another one we need to know is dA. That's a little differential area. And we'll see this definitely in things like Gauss's law and things like that, where maybe we have a certain amount of flux going through our surface. You know, maybe we have a sphere, and there's stuff coming out of the sphere, whether it's electric field, or maybe it's air, or water, whatever our particular topic might be. There's some amount of a substance, or whatever it is we're calculating, that's coming out of the surface of some shape we might be interested in. And so maybe we want to know, what's the total amount of this substance that's leaving this shape? Then we would have to add up the flux through the whole surface area of this particular shape. That's one example where dA might be. Or maybe we have like a window, and we want to know how much wind is going straight through the window. And maybe the wind is not coming nice and perpendicular or orthogonal to the window. Maybe it's coming at some angle theta. And so we want to know, well, how much is perpendicular, and all this kind of stuff. How do we define the differential area? Well, the differential area is an interesting thing because, first of all, you see I've drawn it as a vector. It's got the little vector symbol on top, which means there's a direction to this area, which is something interesting. We don't really think of a directionality to an area. The area of this, room might be, 600 square feet. The area of the surface of a basketball might be whatever it is, but we don't think of an area having a direction. But it's very important for us to define a direction to this area so that we can do things like Gauss's law where we have E dot dA. In order to be able to do a dot product, we need two vectors. We need directions because the dot product is all about how much of one thing points in the direction of the other. And so how do we define the direction of an area? Well, mathematicians have chosen, it's just a standard that was created, and the standard is if you have an area, let's say in the xy plane, so like the area of this square down here that's on the floor, well, it's got an x and y direction. We know how to calculate the area. It's x times y, length times width, and we define the direction of a differential area, or area as a vector, as being orthogonal to the surface radially outwards. Okay, so if this is like a big box, now you're going to see my poor drawing skills, unfortunately. Then the area, for instance, of this front face right here of the box is defined as pointing orthogonal, perpendicular to the surface, outwards of the box. So that is, in this case, it would be in the positive x direction. Whereas this top box up here, this top face of the box, I should say, that's in the xy plane, and its direction for its area is defined radially outwards, which means in this case it'd be in the positive z direction. And likewise, of course, for the y direction in the xz plane. That's just what was chosen. That's the standard everybody uses, and that's what we're going to use, of course. So how do we define the differential area? Well, in the x direction, so in the I hat direction, the area is going to be the other two directions, right? Because the direction of the area is defined as perpendicular to the plane of the surface. So if this is the x direction part of the area, then I need how much of the area is y and z. So it's dy dz in the x direction. And then in the y direction, so that'd be like this surface here, the side of the box. Obviously, it's the x direction and the z direction. So it's dx, dz. That gives me how much is my little piece of area, and that points in the y direction, the j hat direction. And lastly, in the z direction, that's the red one I drew up on that box up there, that area has an amount that's in the x direction and the y direction, so it's dx, dy. And that points in the k hat direction. Okay? So differential area, once you're used to the fact that it has a direction, it is a vector, then the amount that's in each of the directions is just what's perpendicular to that direction. So if you're looking in the x direction, how much of the area is in the x direction? Well, it's the dy dz part. Y times z, that gives me the area, and perpendicular to that plane is the x direction, I hat direction. So now we have our differential length. How far do we go in each direction? We have our differential area, which is what are the two directions that give rise to an area, dx, dy, let's say, and its direction is perpendicular to that area, or perpendicular to the plane which contains the area. And it's defined as outwards. So if you have a box, if you have a sphere, and we're defining the area, the direction, because you could either go positive or negative, perpendicular, the positive direction is just usually defined as outwards from that surface. Lastly, we did length, we did area. The last one is, of course, volume. So d tau, or you might see it as dv, depends on the class, or dq dar, or whatever it is. This one is a little different because this does not have a direction associated with it because it's all three directions. There's no fourth direction for us to have the perpendicular, the orthogonal direction here, because the volume deals with all three of our coordinates. So how do we find the volume of a particular thing? Well, it's just all three coordinates. So if I have a little differential volume, then it's how much is in the x times how much in the y times how much in the z. Right? Obviously, x, y, z, length times width times height, whatever you want to think about it. That's your differential volume. Okay? And that's Cartesian coordinates. That's what we're used to. That's the coordinate system we've been doing since grade school, whether we realize it formally or not. This is how we've done things. And then when you get to calculus and you start having integrals and things like that, we define our differential length and differential areas as like this. Now what we want to do is, of course, how do we do a different coordinate system? And this is where cylindrical coordinates comes in. So let's say we start the same. We have our coordinate system. This is our x, y, z coordinates. We're going to have our point P right there. And it might be that for whatever reason, the Cartesian coordinate system is going to make the math a little difficult here. Maybe what we're dealing with is a cable, a wire, a coaxial cable or something, that has cylindrical symmetry. So that is to say, it's got a length, the z direction, but the outside of our wire is always, it's a tube, so it's always a radial distance away. So maybe we'll have something like, if we imagine a can or a cylinder like this. So there's our cylinder. Again, I'm sorry it's not perfectly straight. And point P happens to be on the edge of the cylinder, or maybe it's a cable, and we're on the outer part of the cable. All right, well, I want to define a vector that points to this point P. So maybe that's our vector there. And I want to know, okay, how can I define this using a different set of coordinates, a different basis set? That's the important word, basis vectors. So in Cartesian coordinates, as we saw over here, our basis is the I hat, j hat, k hat. It's the x, y, z directions. And that means when we call it a basis set, it means that any point, anywhere in our space, can be defined using just those three vectors, or just those three directions, I should say, or coordinates. So if I'm going to change a coordinate system to something else, that means I'm going to have three other directions, three other coordinates, but I still must follow the rule that I should be able to define any point in this space using these three coordinates. And usually what we want is for these basis vectors to be what's called orthonormal. This is one word. It's not a space there. Orthonormal. Ortho means perpendicular to each other. And normal means their magnitude is 1. So over here, I hat, j hat, k hat, they're also called unit vectors because the magnitude of I hat, well, it's got a direction, which is the x direction, but its length, its magnitude, is only 1. So that's why when I have a vector v, I could define it as a certain amount x in the I hat direction. Multiplying x with I hat doesn't change the magnitude of the x value. You know, if I hat had a magnitude of 2, then if I multiply x by I hat, it'd be 2 times x in the I hat direction. So they all have magnitude of 1. They're normal. And their I hat, j hat, k hat are all perpendicular to each other. They're orthogonal. X, y, and z are all perpendicular. So the same thing's going to happen here. I need to find three other coordinates, or maybe not all three have to be different, but a different set of basis vectors that are also orthogonal and normalized. Okay? And here's how we're going to do it. In the cylindrical coordinate system, we're going to steal the z direction as being the same as before. Okay, so again, remember this point P is sticking out at you a little bit. It's a three-dimensional thing. So the amount in the z direction, the height of our point, is still going to be called z. Now, what else can we do? Well, if you remember, when you were dealing with calculus, the first, very first calculus, and when you learned about polar coordinates, so maybe we have a circle, and this is just xy coordinate system, x and y, let's say. Well, we could define a point, some point P, as being a distance r from the origin, radially outwards, and an angle theta, right? R and theta. That defines any point. If I want a point over here, it's some other r, call it R2, and it's some other theta 2, right? But any point, I can define it as r and theta, or I can define it as x and y, right? Two different ways of defining a point. The point's in the same location. It is where it is. I'm just saying, in order to get there, I can either say, and in fact, I'll do this a little cleaner for you. I can either say, here's my point. Let's go a certain amount in the x direction over, and then a certain amount in the y direction up, and I'll be at this point. Okay? That's the Cartesian way of doing things. The other way, which is the polar way, says, let us rotate from the positive x-axis a certain amount theta, and then I'm going to walk out in that direction a certain amount r. If I do that, I reach the same location. So one says, move in the x direction first, then move in the y direction a certain amount, and I'll reach my final destination. Or rotate and line yourself up with a certain angle, theta, and then walk this particular distance, r, and you'll wind up at the exact same place. Two different ways of defining the exact same point. Well, now, that's what I'm doing here with the cylindrical. I've already located the height of point P by calling it a distance z. But what about the x and the y type part? Here's what we're going to do. We're going to use a polar coordinate type thing. We're going to angle out a certain theta, or in this case we'll call it phi, and we're going to walk a certain distance rho. Okay? In order to see it, let me, because I already got the height part down, so now I'm just talking about how far around our little cylindrical base or cylindrical top or wherever we are. The best way to do this is let me pretend like there's some light bulb up here. Here's my little light bulb. And it's shining light. And it's going to cast a shadow of our point down onto the floor. The XY plane is like the floor. And it's going to shine a little shadow straight down to this point right here. Okay. That's not the point P, that's the shadow of the point P in the XY plane. Now, if we look, and I'm just going to make a parallel line like this one here that helped me find Z. Now what I can do is I could say, all right, let this angle that's swept out from the positive x-axis towards the y, remember this is right-hand rule stuff, I'll call this angle phi. And then the distance I travel in that direction, this straight line polar radial direction, I'll call that rho. And so now I can define any point P. So any point P for the vector that's located at point, or that goes to point P, I could define as a certain amount in the rho direction, a certain amount in the phi direction, and a certain amount in the z direction. Okay. Just like before, I did it in the x or the I hat, j hat, k hat directions. Now I have the rho hat, phi hat, z hat directions. Okay. Exact same thing, except a different way of defining this location. Now, what we want to do is figure out, well, how do I know how far I need to walk in the phi hat direction, or how far I need to move around or rotate in the the rho hat direction, how far I need to rotate in the phi hat direction, and so forth. The way we're going to figure this out is, let's define x, y, and z in terms of rho, phi, and z, and vice versa. So first of all, if I have x, y, and z, I know z is already z, right? Z for cylindrical and z for cardinal, that's the same thing. It's the same defined direction, same defined distance. So that's easy. Now the x and the y is the stuff we have to figure out. But look, what do we have here? We've got a triangle made with the x-axis, the the rho direction, and then, of course, if I did this all nice and three-dimensionally neat, the point that connects the two. If I want how much is in the x direction, this part of it, well, here's my phi angle. This is my hypotenuse rho. So the x component that's adjacent to the angle, that's just rho cosine phi. And for y, of course, same kind of a thing. If I want the y direction, which is this part over here, right, if they're parallel like that, this part of my triangle, that's opposite to the angle phi, and opposite from trig goes with sine, so the y component would be rho sine of phi. And there we go. Now we have the x, y, and z coordinate systems defined in terms of our new coordinate system, our new basis vectors, rho and phi and z. If I want to go the other way, what is rho, phi, and z in terms of x, y, and z? Well, of course, z is still z. But how do I find the other ones? Well, rho, that's just the hypotenuse of that triangle. It's the radial distance, it's the distance radially outward from the origin to the point P. And I already know what that is. That's just the Pythagorean theorem. So this is just square root of the x component squared plus the y component squared. And then from our little triangle there, if I want the phi, if I know x and y, then it's just the inverse tangent of the y piece over the x piece. Just like our normal vector stuff, we've done this before for polar coordinates, we've done this before for just adding and subtracting vectors. You add the components together, then you want magnitude and direction. That's all this is. Rho is like the magnitude, phi is like the direction. But it's not the pure magnitude, because of course the magnitude also involves z. But I'm talking about just the shadow cast into the xy plane, which is all we were trying to do there. And so there we go. I now have how to convert between the Cartesian coordinates and the cylindrical coordinate system. And of course we can have problems like if there's some point P, which is defined as 3, -1, 4, give me that point P in the rho, phi, and z coordinate system, the cylindrical coordinates. How would you do it? You would just take these numbers and plug them in. to the equations we have here to convert from xyz to rho phi z, and vice versa. If I gave you the cylindrical coordinate, you need to give me the Cartesian coordinate. But there's other stuff we need to do. So remember when we talked about Cartesian, one thing we needed was the unit vectors, so that we could define a vector v, let's say, points in the I hat, j hat, k hat directions, so it's a certain amount in x, certain amount in y, certain amount of z. We want to do the same thing, but with cylindrical. And here's where something goes a little bit awry. If you think about, and I'll do this on a new page, if you think about, let's say here is the point, one point, let's call it point P1, then the XYZ is whatever it is. The directions for X, the direction for Y, the direction for Z, we already discussed, doesn't change based on where you're locating your point. The directions are fixed. However, that's not true for cylindrical. Notice this. If I have, that's my point P1, then the rho direction points in that direction there. So that's like my rho hat direction. And then my Z direction, that's easy. That's always straight up. And then my phi direction, again, you imagine a circle like the lid of a can or something. And as I rotate around this circle, notice at this point P, when I rotate, phi is changing in that direction there. So remember, this is all kind of, or we would call it tangent to this circle. I can't really do very well with my 3 dimensions. I'm trying to, but there would be my phi hat direction. Okay? So at this point P, rho hat points in his direction, Z points in his direction, phi hat points in his. But if I go to some other point like this one here, now what happens? Now this guy's rho points in that direction. That's rho hat. Now Z hat is still Z hat. That's always straight up. That's not a big deal. And then this guy's phi hat is now that way. Okay, they're still orthogonal. They're still perpendicular to each other, but now which way phi points or which way rho points is different for point P2 than for point P1. So that means my basis vectors, my rho, my phi, and my z, depend on position. They depend on where it is in space I'm talking about. So that means, unlike with the Cartesian, where I hat, j hat, k hat are just I hat, j hat, k hat, no big deal, now I have to worry about what rho, phi, and z are based on I hat, j hat, k hat. So, for instance, let's say I want to know my phi hat direction. What is the unit vector in the phi hat direction? I'm sorry, I keep saying phi hat. Rho hat. The rho hat direction. That's the radially outwards direction. Well, we already know what rho is in terms of everything. Rho is, it has its x component and its y component kind of a thing. Notice rho depends on x's and y's and things like this. So the rho hat direction is going to be, because this is, we're trying to do unit vectors, it's got a magnitude of 1, and it's going to be cosine phi is the x component of rho, and sine phi is the y component of rho. So this is kind of interesting. If I want to write down my unit vector that points in the rho hat direction, and I want to write it down in terms of x, y's, and z's, then my rho hat has two components. It's got an x component and a y component. Of course, it doesn't have a z component because z is its own coordinate. We don't have to worry about him here. So no matter where I am in this plane or in this space, whether I'm at P1 or P2 or some other point, the direction of rho is defined based on where I am in x and y. And where I am in x and y, the x component is cosine and the y component is sine. Okay. Phi hat. Okay, now there's several ways to think about this one. The easiest way is to imagine if rho is the direction that points radially outwards from the origin through this little fake circle I drew. Remember, this is like a can or a cylinder or something. Then phi is tangent to the circle. So that means phi is always 90 degrees rotated, or perpendicular, from rho. And we know the way cosines and sines work in trigonometry, if we have our phi, our angle, is rotated by 90 degrees, then sine becomes cosine, and cosine becomes minus sine. So that means the phi hat direction, the phi hat unit vector, is minus the sine of phi, I hat, and cosine phi, j hat. Okay? That's the easiest way to think about it. If you look here, rho points this way, phi points perpendicular, 90 degrees rotated. And if I rotate my phi by 90 degrees, then cosine becomes minus sine, and sine becomes cosine. That's all I've done. I've just changed phi to phi plus pi over 2, or phi plus 90 degrees. And then, of course, z hat, that's the easiest. Z hat is just z hat. It's the same z hat as Cartesian. So now we've defined our unit vector, our orthonormal unit vectors, rho hat, phi hat, z hat, in terms of the ones we already know, which are the I hat, j hat, k hat directions. Okay? And we're going to see why this is important when we start to have to do things like the divergence or the curl, our vector calculus stuff later on in these coordinate systems. I'm going to have to be able to write down these rhos, phis, and z's like this. But just have this. This is very important. Just have it in a box. We're going to use that later. The last thing we did for Cartesian was we came up with our differential elements, our dl, our dA, and our d tau. Same thing we want to do here. For our differential elements, let's say we have dl. All right, so that means, remember what dl is. It's like, okay, I'm at a point P, and now I'm going to move a little bit to a new point that's just a differential distance away. And I'm going to assume I've moved in, all three dimensions. So that means I'm going to change in the rho hat direction, I'm going to change in the phi hat direction, and I'm going to change in the z hat direction. Well, if I go from, let's say, if I'm looking at P2 down here, from here to, let's say, here, well, my rho has changed by an amount d rho. I just went out a little bit more. So it's going to be d rho in the rho hat direction. No big deal there. It's just a distance. dz, that's the easy one. dz, z hat. But the phi, the angle, that's the one that's a little bit odd. Because if you change by an angle theta, or phi, what is the distance you've moved? I don't care about how much the angle changed. I care about how much distance you've changed. And if you remember, even polar or whatever, if you have a circle, and let's say we rotate about an angle theta here, and this, let's say, is some radius r, then the distance we move, this actual distance, this curved distance here, called the arc length, is equal to r times theta. So if you change by an amount theta, the distance you moved, well, you didn't change by r is still r, but you've changed how much theta is, so I'm going to move a distance, r d theta. Now, instead of r and theta, of course, the defined directions here are rho and phi, but it's the same thing. It's whatever rho we're at, and now I'm changing by an amount d phi in my angle. Oops. And that's the phi hat direction. So again, I've moved from point P to some slightly next to it point, which means I've moved a certain distance. In the rho hat direction, I've moved d rho. In the z hat direction, I moved dz. But in the angular direction, my phi hat direction, I moved by an arc length, and that arc length is rho d phi. Okay, so there's my dl. That's my differential length. The next one, differential area. Well, if we remember how we did it with the Cartesians, let's look at it. In the x direction, it was dy dz. In the y direction, it's dx dz. In the k direction, it's dx dy. It's always, for this particular direction, what are the other two guys doing? So here, if we want in the rho hat direction, then all we have to do is look at the phi change and the z change. Well, the phi changed by rho d phi, and z changed by dz. So rho d phi dz is the area, and the direction of that area is the rho hat direction. Likewise, for the phi hat direction, well, I need how much changes in the rho direction and how much changes in the z direction. Well, the rho direction changes by d rho, and the z direction changes by dz. And then lastly, in the z direction, I need to know how much does rho change and how much does phi change. Well, I'm going to write it in a slightly odd order, but I like the rho out front from rho d phi, and then I have d rho, d phi. Right, again, rho d phi is how much phi changed, and d rho is how much rho changed. And that's our differential area. So it's very easy to get this just by thinking of, if I'm looking in this direction, what are the other two directions changes, and I multiply them. And this is true for all coordinate transformations we're going to do. All right, the last one, d tau. This is pretty easy. Again, you're just multiplying the three changes together, and you don't have any direction. Well, rho changes by d rho, phi changes by rho d phi, z changes by dz. So again, I'm going to stick the rho out front and have d rho, d phi, dz. Again, rho d phi is my phi change. And then I have d rho and dz. Oops. And there we go. There's our differential elements for the cylindrical coordinate system. And now with all of this stuff, what we're going to be doing are things like, del dot v in cylindrical coordinates. We know the divergence in Cartesian. That's easy. That's just dvx dx plus dvy dy plus dvz dz. But if we want this in cylindrical coordinates, well, we're going to have to convert from our Cartesian to our cylindrical, and we're going to make use of this stuff we've written here. We're going to have to write down del operator in terms of rho phi z, and our v vector in terms of rho phi z. And then we do the dot product, and we cancel out what we can cancel out and all of that stuff, and we'll be left with a particular formula for the cylindrical coordinate version of divergence. And unfortunately, it's not as pretty as this one. This one's easy. Cartesian, very, very easy, very, very simple to write down. The equation for the cylindrical one is not as easy to write down. In the front cover, or maybe it's back cover now, of your textbook, it has them all listed for cylindrical, for spherical, and all of that. The curl as well. So you'll be able to check, but I'm going to want you to try to do it yourself. Figure out what should be the equation for the divergence in cylindrical coordinates, and then match it to what the textbook says. One thing I'm going to make sure you're aware of when you're doing this is to keep things in order. The order of operations for derivatives and everything is very important. So if you have, a d by d rho of rho, let's say v phi or something like this, that d by d rho, that derivative, this is a product, so you have the chain rule. You have to do first times derivative of second plus second times derivative of first, all that stuff. So be very careful, and you might have to go the other way. You might have to say, well, this outcome looks like if I go backwards, I could put it together to make it look like this, so it looks a little prettier. Okay? Those are some tricks you're going to have to be aware of when you're doing this, for why maybe yours doesn't look exactly like what the textbook has, but they should be equivalent. And of course, I'm going to do it in class personally with y'all to make sure we understand how to do this. Once we know where the equations come from, how they're derived, then we could just use them later. We're not going to have to derive them every single time we do a problem, obviously. However, it would be a very, very bad thing to just use the outcome and never actually see where the heck the thing came from, because you lose something. You lose kind of the intuition for what's going on if you're just given the definition and you just go with it and you never actually see how did I do it. The practice of actually getting it yourself is going to be very, very powerful for you for doing other stuff later on. All right, anyway, that's the cylindrical coordinate transformation. As I said, you should be able to do things like point P is 3 minus 1, 4 in x, y, z. Tell me what it is in rho phi z, or it's, 5, maybe pi over 2 and 2 in rho phi z coordinates, and I want you to tell me what it is in x, y, z. Okay? You should be able to transform your coordinates using this stuff here, these coordinate transformation, these conversions. Okay, but again, try out yourself writing down del and writing down v in cylindrical coordinates. Then do the divergence, do the dot product of those two vectors, and see if you could simplify it down to match the definition that's in the textbook, or you Google the definition, whatever you want, for the divergence in cylindrical coordinates. And then again, we'll do it in class. Next time, after we do that, we will then go to spherical coordinates, which is a very, very similar process. Instead of z, we're going to have a second angle. So we're going to have r, theta, and phi instead of rho, phi, and z. And so that's going to change things a little bit, but it's the same basic process. We define a point P in the XYZ direction, then define three basis vectors, the r direction, the theta direction, the phi direction, and how do we define them? And then how do we convert from XYZ to r theta phi and vice versa? Then we build up the unit vectors, r, theta, phi, hat. And then we build up the differential elements, dl, dA, and d tau in spherical coordinates. Once we have that done, then we're ready to go start doing some actual electricity, magnetism, and other types of problems that are a little bit more complicated that make use of these coordinate transformations. All right, hope this was helpful. I will see you next time.